We're going to take a look at the cross product, but first we're going to remind ourselves of not the cross product. Remember we saw the dot product in a previous video. The vector a1, a2, a3 dotted with b1, b2, b3 yields a1, b1 plus a2, b2 plus a3, b3, which is a real number. Remember we saw that the dot product can be used in projections and to understand the angle that exists between two vectors. The cross product is something completely different. The dot product is a type of vector multiplication that results in a real number answer, or a scalar function answer in the case that a, b, and c have variable components. The cross product is another type of multiplication, and if we were to find the cross product of two vectors a and b, the result is a vector that's orthogonal to both a and b. That is to say that a cross b gives us a vector c. I'll pause right there to say the dot product yields a real number. The cross product yields a vector. And in the case where we're saying that a cross b equals c, it would be the result that a dot c would be 0, they're orthogonal, and b dot c would be 0. Let's see how the cross product is defined. Suppose we have two vectors, a that has components a1, a2, a3, and b with components b1, b2, b3. A cross b, so it looks like an old school times symbol, and we read that as a cross b, is a determinant. The first row of the determinant are the unit vectors I, j, and k. The second row are the components of A. So A1, A2, A3. The third row are the components of B. So B1, B2, B3. And we compute this determinant the way we would compute any determinant. For the first entry in the determinant, we see that we have the vector I. And to compute the determinant, what we do is we cross out the row and the column that contain I, and what we're left with is a determinant a2, a3, b2, b3, and we multiply those as a 2 by 2 determinant. So the result looks like a2, b3 minus a3, b2 times the vector I, the one that the row and column we crossed out. And I can already see I'm going to need to move this over. We move on to the j entry, and in order to compute the minor of j, we cross out visually, right? Cross out the row and column that contain j, and we're left with a1, a3, b1, b3, and we multiply on the diagonal. So we have a1, b3 minus, multiplying the other diagonal, a3, b1 with a j. Now you may remember from computing determinants that for the first cofactor, we have a positive I times the minor. For the second cofactor, we would use a negative, right? So it's negative a1, b3, a3, b1, j. Then mentally cross out row and column that contain k. We have a plus. And then compute the determinant of the remaining entries there. So a1, b2 minus a2, b1 times k. Looks rather complicated and tedious, but you get used to it pretty quickly. If you're wondering where on earth did they get that, our author gives a presentation that shows that if you were after a vector c that is orthogonal to both a and b, then using algebra you can determine that this would be the result. I'll leave it to you to verify that a is orthogonal to a cross b and that b is orthogonal to a cross b. How might you do that, you wonder? We would take a and dot it with a cross b And you would write that out as A is A1, A2, A3, and A cross B is that A2, A3 minus A3, B2, comma, for the J coefficient here, don't forget we have to distribute a negative. So I'd write that as A3B1 minus A1B3. I need to do a little bit of rearranging here, just a second. And then the Z component would be A1B2 minus A2B1. Form the dot product, see what subtracts out. You'll see that the answer is 0. Let's jump to a quick example here. If A is the vector 2, -1, 5, and B is the vector -4, 3, 8, then we can find A cross B by doing what we just said. The first row of the determinant is I, J, K. The second row is 2, -1, 5. The third row is -4, 3, 8. And in order to compute this, I'll give you the structure that I often write down. So parentheses for a determinant that we're going to write times I minus, because the J component always has a negative in front, right? Parentheses in front of J plus parentheses in front of K, and now I don't have to worry about I, J, and K. Crossing out row and column that contain I, we have -1 times 8 minus 3 times 5. Next, crossing out row and column that contain J, we have 2 times 8 minus -4 times 5, so plus 20. And then crossing out row and column that contain K, we have 6 plus 4. The result is -23I minus 36J plus 10K. And I just caught a mistake. Did you catch it? Did you catch it? So 2 times 3 does give me 6. And then we have a minus -4 times -1. So that should actually be 6 minus 4. So that 10 should be a 2. So A cross B is -23I minus 36J plus 2K. Clearly, it's a vector. You could also confirm that this vector A cross B is orthogonal to A and is orthogonal to B.